Okay. Uh, okay. Thank you so much for your warm welcome and for the invitation for this talk. Uh, okay. So today I'm going to talk about our CPR 2025 highlighted work O-TPT, Orthogonality Constraint for Calibrating Test Time from Tuning Vision Language Models. So before digging into that, let's have a brief idea about what is calibration and why it is important. In terms of if let's say if we consider a perfectly calibrated model in terms of especially confidence calibrated, the model predicted confidence should have to equal to the model predicted true correctness likelihood. So let's understand that with a simple example. So let's think that we have a perfectly calibrated um, neural network classification model, and that model makes a prediction about certain class with a confidence of zero point 0.8. And then at the same time, the model predicted output for that class will have to occur about zero point 0.8 fraction of the time. So which means the model accuracy should have to equal to the model predicted confidence. So it works well in ideal case. The model will be definitely perfectly calibrated in terms of confidence. But in real terms scenario, but it won't be that. So there may have several chances, but we can think in terms of like there may have chance for cross entropy, training bias, overfitting to training data, label noise and ambiguity, and class imbalance and distribution shift. So there may have chance, there may two scenarios or ways. The model can have a miscalibration. So one is for overconfidence and another one for underconfidence. Let's say that if the model is overconfidence, the model assign high confidence for incorrect predictions. Um, it makes difficult for if we are going to deploy any model in real time scenario for like any safety critical application like any, and especially in medical domain or autonomous driving, remote sensing, agriculture. So in that case, if the model makes a wrong prediction, but in that case the model over trust on that prediction, like assigning a higher confidence for that. At the same time, if we consider about if the model have underconfidence issue, uh, the model will make even if it's predicted correct, but but the model will make lower confidence for its correct prediction. Um, so this kind of model will also be a problematic if we are going to deploy that in a real world scenario. So it is uncertain about its prediction. So it may have chance if we are deploy that in a real world scenario, it quickly make a incorrect prediction. So let's understand that with a simple example for a overconfidence prediction. Let's say we are having a model that that predicts on 10 samples. So for let's assume that for all the 10 samples we are having a confidence of 0 0.9. But actually, out of 10 samples of prediction, we are having actually got 10 sample as the correct prediction. So in that case, model we will have overall empirical accuracy of 70 percentage and the overall average confidence of 90 percentage. In that case, there may have a deviation. I mean, the gap between the model average confidence and the empirical accuracy. This is one of the scenario for overconfidence. And if we think in terms of underconfidence, let's take the same 10 samples of prediction. For that, the model makes a confident prediction about, let's say, for all the samples, 0 0.6 as a confidence prediction. But in this case, the model makes only about 8 samples as a correct prediction out of 10 samples. So here we can see that the model reasonably get a good accuracy, but if we think in terms of model confidence, uh, it is really poor. So we can assume that if we do not consider about the model uh, confidence calibration, we can assume that the model have a good accuracy. But if we deploy this model in a real world scenario, it makes question about its reliability, especially in inference time. So there are several metrics are there to measure this error, like SCE, MMCE, ACE, but mostly actively people and researchers are using ECE, which means expected calibration error. So it partitions into bins like 0 to 10, 10 to 20, 20 to 30, up to 100. So it compresses the overall accuracy and confidence into the corresponding bins, and it will give us the average deviation gap between the accuracy and its bins. So if the EC is lower, we can assume that we are having a model with a lower calibration error. If EC is higher, we can assume that the model have really severe calibration error problem. So um, but in order to calibrate the model confidence, there are several existing literatures and methods are therefore, especially in DNS. But in this recent days, mostly researchers and engineers are actively using VLMs like CLIP for many safety critical applications in autonomous driving, medical domain, remote sensing, agriculture, etc. So in order to adapt the model for any downstream task, there's several techniques that they are like prompt tuning, adaptation. So but especially if we are going to adapt the pre-trained clip for in any inference time without any labeled dataset, there's a technique called test time prompt tuning. So they introduced a learnable prompt parameter at the inference time. So they tune or tweaks the prompt parameter at the inference time for a specific sample of input image that given to the model. So according to the model, according to the image given to the model, so it twin the uh, text prompts and try to minimize the entropy, and it will assign a higher confidence for the unknown image that given to the model. So it will eventually helpful to uh, increase the accuracy as well. But this PPDs works on inference time. But it's really crucial to address, especially in inference time, whether we have to check about its reliability. Like if we think in terms of confidence calibration, in because especially in inference time, the model makes a confidence prediction about a certain image that given to it. So if we think in terms of its calibration, I mean, confident if whether it's calibrated or not in terms of in test time. So we use reliability diagram to check whether the model has overconfidence issue or underconfidence issue. So so in this figure you can see the reliability diagram. So the blue color bar plots represents the accuracy. So if the blue color bar plots are below the diagonal, so we can assume that the model has overconfidence issue. If the blue color bar plots are above the diagonal, we can assume that the model has um, underconfidence issue. So in clip, you can see that the blue color bar plots are closely aligned with the diagonal. So approximately it has a lower calibration error like 2.49. And if you see that in a clip adapted with TPT, it has overconfidence issue. So as I stated earlier, the overconfidence issue arises. One of the reasons is the model assign a high confidence for incorrect samples. So in TPD, they use cross entropy to train the prompt, tweaks the prompt parameters. So it works well if the model predicts the correct class and it will assign a higher confidence for that. But if sometimes the model make incorrect predictions, then entropy minimization leads the models to assign a higher confidence. So that's why we believe that so the clip adapted with TPT assign a higher confidence for incorrect samples and tends to model to have a overconfidence issue. So if we consider in terms of existing literature related to calibration for DNN. So why we can't apply that in TPT? So most of the existing uh, calibration related works for especially in DNNs are totally dependent on labeled datasets. And but the problem with TPT is it doesn't have access, or it do not rely on labeled datasets. So we can't use those methods directly in test time prompt tuning. It's because of its reliance on labeled datasets. So this is one of the work from last year ICLR CTP calibrated test time prompt tuning. In this work, they try to reduce the calibration of TPT. So in their work, they try to maximize the text features, which is resulted from text encoder of clip. So their approach is they propose a metric like ATFT. So they show that there's a negative correlation between that. If we in if the text feature is maximized, they tends to show a low. The model tends to reduce ECE. No, so let's understand what this ATFT means with a simple example. So let's assume that in TPT like clip, so the text encoder will output a text feature matrix. Let's assume that the matrix have a shape of 47 by 512. So that 47 means 47 different classes. So we have 47 different class vectors. So they find the mean vector across those 47 different classes. So from that 47 mean vector, they find from that mean vector, they try to maximize the each of the class vector from its mean vector. So throughout that, they find the norm that is called ATFT. So they proposed a plug and play loss function with this ATFT to work with TPT loss. So with that, they show that they reduced ECE across the datasets they performed. So there is another work from ECC last year. So their method is that from their empirical analysis and their motivation, they suggest that if the logic norm or logic range increased, the ECE also getting increased. I mean, so they told that from their motivation, they formulated three formulations with the same objective. So what they did is they utilized the pre-trained clip maximum and minimum range. So with that logic range, they adapted the logic resulted from PPT or COOP. So their method is not directly reduce the ECE. So they use the loss. They use their loss or any scaling. So there's three methods with the same objective with CTPT. With the combination of CTPT, they reduce the calibration error furthermore than CTPT did. So with this work, so we try to learn and understand what the intuition behind this problem and how we can tackle this more effectively. So as we can see here that from our empirical analysis, we first find the cosine similarity between the class vector that I told earlier for the example for CTPT. Let's assume that 47 by 512 matrix, we find the mean cosine similarity between each of the different class vectors, and we find the correlation between that cosine similarity and ECE. We figured out that when the ECE and the cosine similarity between each of the different classes get reduced, ECE also get reduced. So we further emphasize that our intuition with another figure from the right hand side, the probability density function of cosine similarity for different hard prompt styles. So in here we used to choose different hard prompt styles like a photo of a specific class or image of a specific class or or a beautiful image of specific class. Like we used to choose different hard prompt styles, and for each of the hard prompt styles, hard prompt styles, we figure out the cosine similarity and its corresponding EC. And it shows that the prompt which have a low cosine similarity between each of the different class vectors, it tends to reduce ECE. So what it tells us that more intuitively that when we emphasize or encourage the orthogonality between each of the class vectors, it reduces ECE. So it means that maximizing the angles between each different class vectors. So let's understand with the hypothetical figure to understand this idea a bit further. So as you can see in this figure, if we consider the CTPT, in the success case of CTPT fields, we find that they try to maximize each different class from its centroid. But in some cases, in some cases, if they are different class vectors clustered together, they may have chance, the model have chance to predict the incorrect classes, which are called that it collapse with the correct classes. So in that case, the model may tend to give higher confidence throughout the entropy if it choose incorrect classes. So therefore, our orthogonality constraint that I told earlier from our empirical motivations, we maximize the orthogonality constraint between each of the different class vectors. So with the approach, we propose these formulations, uh, orthogonality constraint. So is the text feature matrix, and I is the identity matrix. So we propose this formulation, and lambda is the strength of that. We use to choose 18 across all the datasets we use for that. So for our experiment, we use clip B16, VIT backbone, and clip ResNet 15, and we used to evaluate across fine-grained datasets like around 11 datasets: food, DPD, pets, cars, ImageNet, Caltech, and so on, and as well as natural distributions datasets like ImageNet A, V2, R, S as well. And we evaluated across accuracy, expected calibration error. So for in this slide, I'll show the results of accuracy and SE. So if you want to know more about experiments and further results, uh, you can find our paper from this year's CVPR or OTP. So as I have mentioned the GitHub link as well here, the QR code. So here's our results. So we evaluated across all the baseline that exists for TPT and the datasets. So for all the learned datasets for clip B16, or CTPT got 5.13 and we got 4.23, and we managed to maintain the accuracy of across all the datasets as well. And in some cases, if we consider the zero shot got at all the data across all the data set 4.43, but even we beat the zero shot performance as well. And when if we consider the ResNet, also we beat across all the baseline that already exists for that. For CTPT got 6.19 and we got 5.45. For in this case also we have a good performance than a zero shot as well. So not only then clip, so we use the trained weights of hoop and adapt that in a test time. So for that as well, we get good performance than CTPT what did. And for Maple multimodal prompt training, so this is a recent work. So we use their trained weights and adapted in TPT. So for that as well, we got 4.11, and for the direct TPT West Maple got 6.94. So for natural distributions datasets, like we got a good performance, 4.88 and 9.69, something like that. So if you see throughout the reliability diagram, when comparing with CTPT and OTPT. So in most cases, we reduce the overconfidence for the DTD and Flower datasets than what CTPT did, as well as we reduced the um, underconfidence issue of that as well. So in conclusion, I can say that the OTPT improves the calibration in test time prompting without any requiring of supervision, labeled datasets, and orthogonality and enforcing orthogonality constraint across textual features leads to more reliable confidence estimates, and we are reducing the EC across all the datasets and backbones and domain shift. So in future direction, it's good to explore for any dynamic from regularization. So adjusting the orthogonality strength based on any uncertain image or any hard features image when it given to the image, and it's important to explore any application related domain like medical imaging or safety critical applications like autonomous driving. So I believe that is one of the crucial issue to address it in terms of in uh, application related side as well. And thank once again, thanks so much for your invite to this talk. So yeah, for I'm glad to happy to answer for if you have any question.
Fantastic. So we do have one question that came in early, right before you started double clicking on overconfidence. And the question was, what do you mean by confidence of a classification model? Is it the output of the model for an input belonging to a particular class or something else?
So the confidence means the model predicted probability confidence for the certain class. The model predicted certain class. So let's assume that at the output layer, so after we got logics of distributions. Let's say we are applying softmax function and we are getting this distribution of uh, classes. If we are using five classes, we will have a five distributions. For that, we will get the confidence for each of the classes. So I mean that corresponding image, if the model gets predicted for the corresponding class, so we will have a certain confidence for that specific class.